Okay, welcome back to statistics. And so today we are going to continue on with part 2 of the rules of probability. And so today we're going to talk about the other rules of probability, which deals with the multiplication rules. And this deals with when we connect two events with an AND statement. So we're looking for the probability of A and B as opposed to before looking for the probability of A or B. So here we're going to look at what do we do when we have A and B. So we're going to be looking for the probability of that. And so we're going to talk about the two rules that deal with this situation. Okay, just like before there were two rules for OR. We had the general addition rule and then we had the simplified addition rule if the two events were mutually exclusive. Okay, so we're going to talk about the two multiplication rules dealing with AND now. Okay, so the general multiplication rule works for any situation where you're looking at an AND. Okay, it's going to be the probability of A and B is equal to the probability of A, okay, then times the probability of B given A. Okay, so this is actually, if you remember, this is actually directly from the conditional probability definition. Okay, so if you remember, the definition of conditional probability was the probability of A given B was what? The probability of A and B divided by the probability of B, right? Well, in that case, we just solved for A and B. So we just multiply both sides by the probability of B, right? And we get the same thing. Okay, so this multiplication rule is derived directly from what we talked about earlier, which is conditional probability. Okay, so this general rule will work for any situation dealing with the two events, the probability of two events that are connected by AND. So the probability that both events will occur at the same time. Okay, and so in this definition, it does not include anything about independence, and that's what we're going to talk about now. So this will work for any case for AND, okay? But the simplified rule deals with independence. And so what happens if A and B are independent? Well, what happened to the conditional probability when A and B are independent? It just reduces to just the probability of the event that we're interested in. In this case, it doesn't matter if we know that A has occurred or not, it's still going to be just the probability of B. So it just becomes the probability of A times the probability of B. So it just becomes the product of the individual probabilities of the separate events. And so that's what we're going to use if we know that the events are independent. And so that's the question we're going to ask ourselves anytime we have a situation that deals with AND. We're going to ask ourselves, hey, are these two events independent of each other? Okay, and the other thing I want to also mention is just with these two rules can be applied to any number of events. Okay, so if I also wanted to extend this out to the probability of 3 events occurring, A, B, and C, right? So A and B and C. So these rules can be expanded out to more than 2 events, and also with the addition rule as well. Okay, so these can be extended out. So now let's just give me an example. So if we're looking at 3, then we would look at, for the general rule, it gets a little bit more complicated. So we don't usually do any more than 3, especially in a basic stats class. So it's going to be, if we do A and B and C, right? Then this would be equal to, since we're not talking about independence here, it'd be the probability of A, right, times the probability of A, right, the next one, so A, B, let's just say we're doing A first. So probability of A, then times probability of B, given that A has already occurred. And then we're going to multiply that by the probability of C, given that A and B have already occurred. So it's A and B. And so we get a more complicated way of doing that. Okay, and then once we look at these, we can just go ahead and apply the definition of probability here. But again, if they're independent, right, if they're independent, then it just becomes the probability of A times the probability of B times the probability of C. Okay, so again, it can be applied to more than 2 events. Okay, and likewise, with the addition rule as well. Okay. Okay. Let's do an example. So let's say we have let's do this. Okay, let's do this one. I don't want to do the same one. Okay, here we go. So a community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The rest are novice swimmers. 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. And 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. Okay, so let's create a table using this. Okay, so here we have 150 members. So they're either going to swim, they're either going to practice 4 times a week, or they're not. And they're either going to be advanced, intermediate, or novice. So let's set up a contingency table showing this. So we have, and you can set up the contingency table different ways. Okay. Oops, hold on. A little too big. Do that, like that. Okay, so now we're going to do the type of swimmers here. So we're going to do advanced, intermediate, and novice. And then over here, practices 4 times per week and doesn't. So let's do it this way. So we'll say yes, no. Okay. And so here's going to be the column totals, or excuse me, row totals. And these will be the column total. Okay. So let's just fill in the table with what we have. Okay. So it says 150 members of the swim team. So here's 150. That's going to be our grand total. Okay. We're going to, if we total all the column totals or all the row totals, that's the total, the grand total. Okay. So we'll call this the grand total. And so 75 of the members are advanced swimmers. So 75 are advanced. So that means this total here for advanced should be 75. And 47 are intermediate. And the rest of the 150 are novice. So what does that give us? That gives us 75, 122, right? So then 122, that'll give us 28. So let's make sure this adds up. So 70, 110, no, okay, something's not adding up, right? 75, 125, 122, no, that's right. So 70, 110, 130, 145, 150. Okay, good. So now, 40 of the advanced swimmers, okay, so 40 of these swimmers practice 4 times a week. So 40 of these swimmers, so 40 go here, which means what's left over for the ones that don't practice 4 times a week? Well, it'd be, so 75 minus 40, so it'd be 35, okay? And then it says 30 of the intermediate swimmers. So 30 of these guys practice, which means 17 is left over. And then 10 of the novice swimmers practice, which means 18 are left over. So now all we have to do is fill out the row totals. So this adds up to 30, 40, 50, 65, 70. And then of course what's left over is going to be 80. Okay, and of course this adds up to 80. Okay, so now that we've got our contingency table filled out, now we can answer probabilities. Okay, so what do they tell us? Well, let's see what the questions are. So it says, what is the probability that the member, okay, so it says, suppose one member of the swim team is chosen randomly. And then it says, what is the probability that the member is a novice swimmer? Okay, so we want the probability that the randomly chosen person is a novice swimmer. Well then, looking at the contingency table, we have to say, hey, out of the total number of swimmers, how many are novice? Well, 28, right? Out of 150. So the probability is going to be 28 out of 150, and that probability turns out to be 0.187. Okay? So now the next question says, what is the probability that a member practices 4 times a week? So now we're interested in just swimmers who practice 4 times a week. Well, this would be the yes column. So it'd be the total 80 out of the total number of swimmers, which is 150. So the probability of a randomly selected swimmer from the 150 who practices, that practices 4 times a week, so, or we could just say P for practices, we could just say P represents practices, right? Double P might be confusing, but just, so practices 4 times a week is going to be, how many swimmers practice 4 times a week? 80 out of the 150, and so that probability is going to be 8/15, or 0.533. Okay, so now, so the contingency table is very helpful in letting us use the definition of probability. Okay, so right now, just so you know, what definition of probability are we using? We're using the empirical definition of probability. We're taking the number of the number of people, right? The data. We're using a data set, and so we're using the relative frequency definition for probability. Okay. Okay. Now it says, what is the probability that the member is an advanced swimmer and practices 4 times a week? Okay. So we want this, right? So let's say advanced swimmer and practices 4 times a week. Okay, so the probability of A and P. Okay, well, let's use the rule, the general rule, right? Because it's not the case that these are mutually, or not mutually exclusive, but these are independent of each other. These are not going to be independent of each other. Okay, so in this case here, let's just use the general rule. Well, the general rule says what? Well, we're going to take the probability of A times the probability of P given A. But let's use the contingency table. Before we even apply this here, let's see if we can do it without the formula. Okay? What is the probability of A and P? Well, let's just look at the contingency table. Okay? How many people, how many swimmers are both advanced and practice 4 times a week? Well, all we have to do to find that number is just use the table and find where the column and the row intersect each other. So we're going to look for advanced and practices 4 times a week. So here's the advanced column. Here's the practices 4 times a week. And so we find that there are 40 swimmers that both practice 4 times a week and are advanced swimmers. So it's going to be 40 out of how many? The 150 swimmers. And so what do we get? We get 4/15, which is going to be approximately 0.262. Because it's just half of the other one, right? Nope, 266. That's right. Forgot, it's supposed to add 266. Okay, so it's just half of this. Okay, so if you double this, you get that. Okay. Okay, so let's go on. Let's talk about more. So it says here, the next one says, hey, what is the probability that a member is an advanced swimmer and an intermediate swimmer? So what's the probability that a randomly selected person is an advanced swimmer and an intermediate swimmer? Well, is it possible that one randomly selected person is going to be both an advanced swimmer and an intermediate swimmer? Of course not, right? You're either going to be one or the other. You can't be both. So this probability is going to be 0. So what does it tell you about these two events? They're mutually exclusive events. They cannot happen at the same time, right? By definition, okay? Okay, so now, E says, are being a novice swimmer and practicing 4 times a week independent events? Why or why not? And I already gave you the answer to this, but let me explain, okay? They're not advanced, they're not independent of each other. because one will affect the probability of the other. In fact, it says here, it says, if you take the definition, right? So let's take the definition of being, well, let's see if I have here. Let's do this. We can prove it by using the definition of independence, right? So what do we know about independence? Well, to be independent, we know that these two probabilities, right, have to be the same. So if I go, so practice A and P, so no, let's do novice. So novice and practices 4 times a week, right? So we found novice and practice 4 times a week. Well, where's the novice? Novice is here, right? Novice and practice 4 times a week is 10 out of 28, right? So that's 10 out of 28, okay? So now, remember that if it's going to be independent, then probability of N and P should be equal to the probability of N times the probability of P. Okay? These two should be the same probability. Okay? Because this comes from the fact that if they're independent by definition, probability of A given B, right? Well, let's choose, A given B is equal to the probability of A times the probability, oh, let me just make sure I'm doing this right. Oh, no, that, you're right. Okay, this should be equal to this, and the probability of B given A should be equal to the probability of B. Okay, well, these two satisfy this. Okay, so we know that this is equal to what? 10 over 28. So that's 0.357. Hold on a second here. Novice and practices 4 times a week. Oh, I'm sorry, not 28, 150. It's 10 out of 150. I'm sorry. Yep, I forgot we're not doing 28. Sorry. So scratch that. Remember, the 28, I just got focused on this. Remember, it's a random person out of the 150, not out of 28. So this should be 150, and we get 0.067. Okay? Now, if we take the other probability and say, okay, well, the probability of being a novice and times the probability of being or practicing 4 times a week, well, if we take those two probabilities, which we already calculated those, this was 40 out of 150, right? So, or not advanced, 10 out of 150, right? So being a novice, 28 over 150. Okay, so being a novice is, how many novice do we have? 28 out of the total 150 times the probability of practicing. We found that one too. It's the how many people practice. It'd be 80 out of 150, right? So 80 out of 150. So these two should add up, or excuse me, multiply to the same number if they're independent. So we get we get 0.0996 or 0.100. Okay, so Those two are not the same, therefore they're not independent, okay? So remember the definition of independence, okay? So this is going to be a good review here. So remember that for independence, we have to have, one, the probability of A given B has to equal the probability of A, and the probability of B given A has to equal the probability of B. And in other words, what this implies is the probability of A and B has to equal the probability of A times the probability of B. Because remember, in general, the probability of A and B is the probability of A times the probability of B given A, right? But this is also equal to the probability of B times the probability of A given B, okay? Because we can write this way or this way, okay? So again, if these two are true, then they both will add up to probability of A times the probability of B times the probability of A, okay? So in other words, you can just test it by using this. Does the probability of A and B, is that equal to the product of their probabilities? Okay, so now you've got another way that you can test independence. You can use the definition and test these, or you can test this as well for independence. Okay? Okay, so now let's do one more example. Let's see here. Okay, let's do this one. It says, studies show that 1 woman in 7, so approximately 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. Now let B, okay, so let B be woman develops breast cancer. So the event that a woman develops breast cancer is going to be B. So woman develops breast cancer. Okay, and then let N be the test is negative. So they take a diagnostic test, right? They test for breast cancer and it comes out negative. So N is the test is negative. Okay. Suppose that 1 woman is randomly selected. So let's just suppose we select 1 random woman from the population. So now it says A, what is the probability that the woman develops breast cancer? Okay, so that's it. So what's the probability that the woman develops breast cancer? The probability of B. Okay, well, what is that? Well, based on the information, what do we know? Okay, so we know that 1 in 7 women who live to be 90 will develop breast cancer. Okay? So we know that the probability of a woman having breast cancer is approximately 143. Okay? So that's it. That's the answer, right? They gave it to us, right? So the probability, that 14.3% is the probability of getting breast cancer. So that's it, 0.143. Okay. Now the next question, part of that is, what is the probability that a woman tests negative? Okay. So in general, what's the population, or based on the population, we want to know what is the probability that the test is negative. Okay, so in general, what does it say? It says that the test for breast cancer in the general population is negative 85% of the time. So the probability that a test is negative is equal to 0.85, so pretty high. Okay? Now, B says, given that the woman has breast cancer. Okay, so we know that the woman has breast cancer. Given that the woman has breast cancer, what is the probability that the test is negative? So we want what is the probability that the test is negative given that the woman has breast cancer? Okay, well, what is that probability? Well, they give that to us too. They say, it says that suppose that of the women who develop breast cancer, so of the population of women who have breast cancer, it says the test is negative 2% of the time. So that's the probability right here. Given that the woman has breast cancer, so the population of women who have breast cancer, the probability that the test is negative is 0.02. Right? So it should be very small. And that makes sense because if we're talking about all women who have breast cancer, and we know that they have breast cancer, we should get a very low probability of getting a negative result, right? That would be what we call a false negative. Or excuse me, a false negative, right? So saying that they don't have breast cancer when we know they really do. Okay, just keep that in mind. So this is correct. So B is that probability. Now C. What is the probability that a randomly selected person has breast cancer, or a randomly selected woman has breast cancer and the test is negative? So this is what we're looking for. Probability of having breast cancer and the test is negative. Okay? So this is not conditional. We don't know if the woman has breast cancer or not. Right? So in this case, we want to ask ourselves, is it independent? Well, we don't know yet. Let's find out. Okay? So let's use the definition, the general rule of probability, the multiplication rule. And so we're going to do the probability of B times the probability of N given B. Okay, now, do we know these two probabilities? Yes. We just got them in A and B, right? So this is going to be the probability of B, which is 0.143, times the probability of N given that she has breast cancer. We know that's 0.02 from part B. And so if we multiply these two numbers together, we get 0.0029. Okay? So this is just using the general rule of probability. We don't know anything about independence. Okay? Now, what is the probability that a randomly selected individual or woman has breast cancer or the test is negative? Now we're talking about an or. So again, we should be talking about the addition rule. Okay? So in this case here, now we're not talking about mutually exclusive events. So let's just assume that they're not mutually exclusive because it is possible, right? It is possible that they could happen at the same time, right? We just found that probability. It's not zero. Okay? So now we're going to use the general rule of probability, which means we're going to take the individual probabilities and add them. So probability of having breast cancer plus the probability of a negative test minus the probability of both. So B and N. Okay? And we know all of these. Okay? So we know this one is 0.143 plus the probability of n, which is 0.85, minus the probability of b and n, which we just found is 0.0029, or 0.003, if we want to stick to 3 decimal places. So now if we add these together, we get, and subtract, we get 0.990 as our probability. Okay? So that's using the general rule of the addition rule, the general addition rule. Now here's the thing. Now we know from this that these are not mutually exclusive, right? So these are not mutually exclusive. Why? Because this probability is not equal to 0. Okay? Let's see. And that's it. Okay, and that, I'm going to wrap up part 2. So that's really just a couple of examples on how to use the multiplication rule, the general rule, and the simplified addition rule. So again, just remember that the question you want to ask yourselves when you're dealing with the general multiplication rule and the simplified multiplication rule, so when we're dealing with events that are connected with and, is the first question you want to ask yourselves is, are these mutually exclusive? If it's not told to you that they're independent. So again, let me restate that. If you have two events that are connected by and, the question you want to ask yourselves is, are they independent? And so if you're told specifically that they're independent, then that's fine. If you're not told that they're independent, or it's not reasonable to assume that they're independent, then you can't assume that they're independent. Assume that they're not and solve it using the general rule, okay? So that will wrap up this part of the general rules of probability. So then this will wrap up this section. So again, just to recap, you've got the four rules basically. You've got 2 rules for dealing with or statements, events that are connected with or, and you've got 2 rules that involve statements connected by and. If you have or statements, then you want to ask yourselves, are the events mutually exclusive? Okay, if they are, then you can simplify it significantly, okay? If it's an and statement, you want to ask yourself, are these events independent? If they are independent, then you can also use the simplified multiplication rule. And again, remember, these rules can be applied to more than 2 events, so 3, 4, and so on, okay? So if they're independent, then it just becomes the product of however many different events that you're considering, okay? If it's a or statement and you have multiple, like 3, 4, 5 events connected by or statements and they're mutually exclusive, then you're just adding up their individual probabilities, okay? So that's where we'll end it. If you have any questions, again, just reach out to me or review the tape again, go through some of the examples in the book, and I'll see you next time. Have a good day.